Yeah, hi everybody. So it's 8 p.m. somewhere in Great Britain, and so I would like to welcome all of you to this VSA online webinar. So today we have kind of two shorter talks given by Mikael Hersche and Geethan Karunaratne, and soon I will give the floor to them. But I want to make a couple of announcements before that. I will double these announcements as well in the email list, but I want to say it loud. First, probably you have noticed, so now the schedule is finalized for this season of webinars, and the last webinar is scheduled on December 19th, and it is currently stated that it is work in progress session. So the idea was coined by Rose Geller, and I think it's a good idea to invite people for more of a panel brainstorming session where we will have some pitches of ongoing work, something really exciting and cool. So if you feel like contributing to this work in progress session, so please drop me a line. And as I say, I will duplicate this message in a separate email. And secondly, also in December, I would like to organize a kind of demonstration session. So less of paper presentation, but more of really something, a session where you can present some practical outcomes of VSA HGC work. And this demo session will be held, or is planned to be held in Melbourne. So if you want to demonstrate your solution and you think that it's kind of cool and outstanding, so please contact me for that. And this message also will be duplicated in a separate email. All right, I should stop talking now and give the floor to Mikael. So please.
All right, so we share the screen. So I hope you can see my screen, right?
Yes.
All good. Okay. Yeah, so hello everybody. I'm presenting the work with the title Constrained Few-Shot Class Incremental Learning. So this is going to be a two-part talk where we essentially mainly showcase how VSA can enhance continual learning approaches. I will show more the algorithmic side, and then Geethan will show how these techniques can then be used to efficiently deploy continual learning algorithms on hardware. So as I already said, we target continual learning. So this is essentially the task where a learner needs to extend continually its knowledge as time goes on. So let's say learner needs to learn two tasks sequentially. Task one might be distinguishing between, let's say, cats and dogs, and the task two might be distinguishing between airplanes and cars. So we might provide our learner some examples of task one, meaning cats and dogs. And of course, with like gradient-based learning and backpropagation, we're able to improve on the loss function and safely distinguish between cats and dogs. At the same time, we don't really learn something about the airplanes and the cars, of course, right? Because we don't show any examples. So we might now show like also examples from task two. Of course, also there we can improve the loss function such that we can distinguish between the classes in task two. However, at the same time, we seem to not be able anymore to distinguish the classes in task one. And this effect is also known as catastrophic forgetting. This is really one of the major issues in continual learning. It can even become harder when we tackle an even more difficult problem, which is called few-shot class incremental learning. So there, the learner is only exposed to just a few examples or shots from previously unseen classes, and it needs to extend its knowledge. So let's say we have a learner and it has a knowledge which is here represented with this black bar, and now it needs to extend its knowledge such that it also can recognize green cylinders. So it updates its knowledge, then it might also encounter blue cubes and also update its knowledge based on that. After it extended its knowledge, it always needs to be able to classify or recognize all the classes or objects that it has been exposed so far. So there can be multiple of those, we call them sessions, where we extend the knowledge of our learner. And always after extending the knowledge, we need to be able to classify or recognize all the classes that we have seen so far. So we have already seen now that having just a few examples or shots per new class is quite a restriction or a challenge. We go even a step further and put some constraints on the learner such that it is practical and can be deployed to a resource-limited device, let's say at the edge in a mobile device. So we already have seen that given by the practical future class incremental learning, the number of samples per class are limited because sampling and labeling is expensive. And we also put some more constraints like on the memory. So the memory footprint of our model should grow at most linearly with the number of classes, and also the compute efforts to update our learner such that it also can distinguish new classes should remain constant as we encounter novel classes. Overall, with all those constraints, we call our new paradigm constraint few-shot class incremental learning. And our approach to tackle this very challenging task is to use an architecture that consists of a frozen feature extractor, a optionally retrainable fully connected layer, and an evolving explicit memory. So this feature extractor and the optionally retrainable fully connected layer have been pre-trained and meta-learned. I will show in a second how this works. And as they are already prepared to solve this task, we then simply, as we encounter new classes, we simply write them as an average prototype in the evolving explicit memory. So we encounter a dog, which is marked with blue, then also a cat and a chameleon, and they are all written into the evolving explicit memory. So overall, this explicit memory has simply one entry per class, or like one prototype. A bit more in practical terms, the feature extractor in our case is a ResNet 12, and then you have the fully connected layer and the explicit memory, which is evolving. So now the question and really the secret sauce is how do we prepare our feature extractor and the fully connected layer such that they can accurately distinguish between different classes. And the key here is really a novel meta-learning approach that ensures that we have quasi-orthogonal prototypes in our explicit memory. So we have multiple of those meta-learning episodes, whereby one episode is that we first sample a couple of shots from each of the classes. So here we have two classes, dogs and cats. We pass those images through the feature extractor and fully connected layer and write the average prototype vectors into the explicit memory. Now, in the next step, we want to train or update the fully connected layer and the feature extractor such that the output of different classes is quasi-orthogonal. Why do we aim for quasi-orthogonality? So if the dimensionality of those prototype vectors is large enough, we never run out of quasi-orthogonal prototype vectors. Hence, we have little interference between the prototype vectors and achieve high classification accuracy, as we will see later. So how do we then update this feature extractor and the fully connected layer? We simply first draw again a sample from our training set and a query image, pass it through feature extractor and fully connected layer. We compute the cosine similarity between the prototype vectors and the query vector. We pass it then to a soft absolute activation, which essentially embraces the quasi-orthogonality between the vectors in our explicit memory. We then compute the negative log likelihood loss and backprop through our architecture and update the feature extractor and the fully connected layer. And this step, meaning sampling some support images, write them into the explicit memory, and update the feature extractor and fully connected layer, is done multiple times until we converge to a good solution, where hopefully the content of our explicit memory becomes quasi-orthogonal. So as the meta-learning phase is finished, we can deploy our algorithm into the wild. So first of all, we had this base session where we already have used those examples for doing the meta-learning. So we write our explicit memory based on the content of the base session. And hopefully, of course, there we will have close to orthogonality in our explicit memory. As we then encounter novel classes, let's say a chameleon, we also pass it through the feature extractor and the fully connected layer and write that vector into the explicit memory. And there we, of course, hope also that we have almost orthogonality, but this is not guaranteed anymore because we did not optimize for it. For doing then the classification, we simply pass the query image through the feature extractor and fully connected layer and compute the cosine similarity and pick the class with corresponding highest cosine similarity. So we call this approach mode 1. We will have different modes. So this is really the simplest approach with just doing prototype averaging, whereby both the feature extractor and the fully connected layer are fixed. So here in this chart, we show the performance on the mini ImageNet dataset. This dataset has 60 classes in the base session, so where we could do the meta learning, and then we always add 5 classes within a session. Overall, we will have in the end 100 classes that we need to be able to recognize. Here on the y-axis, we see the accuracy, whereby we see that we always have 5 shots or 5 examples per class. We compare our approach to 2 baselines, which are state of the art, and one from University 21 and one from CVPR 20. So if you look at the accuracy of at the base session, we see that we already outperform both of the baselines. And as novel classes are added, of course, the accuracy goes down because the task becomes harder. However, still we outperform both the baselines in all cases. So just quickly to take one step back. So our CF-SEL in mode 1 has really minimal memory requirements because the only thing that is expanding is the explicit memory. However, this is really the minimum that one needs to distinguish between n classes. We need to have n hyperplanes. Moreover, for doing the updates in our explicit memory, we just need to compute average prototypes. So we don't need to do any backpropagation and gradient updates. Moreover, it can be even more optimized by using the physical properties of our analog AI, which Geethan will then show later on. So the question is, can we do better? And the answer is, of course, yes. So we can further improve the orthogonality. And what we do there is we do retraining of the fully connected layer. So as I already said, with the classes from the base session, we achieve quite good orthogonality in our explicit memory. However, as we encounter examples from novel classes, orthogonality is not guaranteed anymore. So what we can do is just retrain this fully connected layer such that we have, again, an orthogonal representation or quasi-orthogonal representation in our explicit memory. And we have different update mechanisms. I will, so we call them mode 2 and mode 3. I will show mode 3, and in this mode 3, what we have in addition is a global average activation memory. So as the name suggests, here we simply store the average activations per class. This is similar to what we store in the explicit memory, just one layer earlier. So now we have kind of a two-step approach. The first step is to update the content or the prototypes in our explicit memory, which gives us new target prototypes. Those target prototypes show better orthogonality while still not diverging too much. And we can achieve this by solving an optimization problem with kind of these two loss functions with orthogonality while still not diverging too much. Then in the next step, we update the fully connected layer such that given the content of our global average activation memory, if we pass it through this fully connected layer, we want to have those kind of new mapped prototypes to be close to the target prototypes. One short comment about the memory footprint of this mode 3. Even though we need here, it seems that we need additional global average activation memory. And if we store the activations here, we actually don't need to always store the content of the explicit memory. We can rematerialize it just by passing the content of the the global average activation memory through the fully connected layer. So let's have a quick look at the performance on mini ImageNet again. So we already have seen before the performance in mode 1. And if you compare to mode 3, we see that it mainly enhances the performance of our CIL in the presence of large number of classes. So there you really see that if we have large number of classes, there is a lot of interference between the prototypes because they might not be that orthogonal anymore. Thanks to this mode 3 and the update of the fully connected layer, we can improve it further. And this also motivated us to test our approach on even large number of classes. And we did this on the omniglot dataset. So we casted this omniglot dataset as a few-shot class incremental learning problem, where we have 423 novel classes on top of the 1200 base classes. So overall, in the end, we need to distinguish between 1623 classes. We also set up two baselines, and if we compare it to our mode 1, we already see that our mode 1 improves already with comparison to the baselines, and also the mode 3 further enhances it. So we really see that in presence of large number of classes, our mode 3 is really beneficial. So overall, we can really say that our CFSL sets a new state of the art in few-shot class incremental learning. First of all, because it has really minimal memory requirements. So in all the modes, the memory of our approach grows linearly with the number of classes. We have low computational requirements. So I have shown you two modes. In mode 1, we just have simple prototype averaging, which will be almost for free on our analog AI, as will Geethan show. And in mode 3, we have simple fully connected layer retraining. So, and there we have really low number of updates, and we have experienced that less than 50 updates are way more than sufficient. And we achieve new state-of-the-art accuracy in 3 benchmarks. So I've shown you the mini ImageNet benchmark, and same trends are also visible in the CIFAR 100, where in both cases we have 40 novel classes. And then we have also shown the first few-shot class incremental learning application on the omniglot, where we have up to 1623 novel classes. So with this, I would like to conclude my part, and I would say I can also already answer some of the questions before we go over to Geethan's talk.
Yes, let's do a quick question session while we are swapping the screens. So anybody? Yes. So let's see. Well, I suggest we continue and then we return with the questions, even for the first half of the talk at the end of the second talk. So, Geethan, please.
Hi, everyone. Thanks very much for this opportunity for us to present our work today. Yes, as Michal mentioned, so this is a kind of a sequel to the work that Michal just presented. And this is about how we implement this continual few-shot learning algorithm on this in-memory computing analog AI hardware that's also developed at IBM Research. So yeah, because of this reason that it involves this quite complex hardware that has been developed, this is kind of a collaboration of multiple research labs of IBM Research, as mentioned in this slide here, and was also presented in one of the sessions at the ESSEC, this conference which held together in Milan this year, this month actually. Right, so let's move on to some motivation why we need to look at this kind of a problem. So as we all know, human brain is the most efficient hardware out there which can do continual learning, as you can see in this graph here, starting from very early age, where we start learning some very basic concepts of shapes. Growing to a childhood, we learn even more concepts like, for example, the toys that we encounter in our life. And growing up, even into our grown-up age, we learn even more complicated concepts or complicated objects, and we be able to distinguish all of them at this grown-up age, using the power of the brain. And we all know that we can do all these distinguishing different concepts, classes, while dissipating a constant amount of energy and this remains to be the case for a very long period of time, up to, let's say, like 8 years or so. And we constantly dissipate the same amount of energy while being able to distinguish more and more new concepts and objects. So how can we bring this knowledge of how the brain functions into building or fabricating energy efficient continual learning hardware? So this is a question we try to answer with this research. So there are several approaches that have been tried. And one of the promising approaches is what we call this non-volatile memory-based hardware. As you can see in these graphs, so in this quite recent years, it has been shown that this hardware that has been developed using non-volatile memory is performing, it can achieve a quite low energy values when it does the inference operation. So here, what it exploits is the fact that we can process this matrix vector multiplication operations of an inference task using these analog in-memory computing techniques. And as you can see here, it can also give us high energy efficiency compared to other available hardware, SRAM CPU, GPUs, and also the static power that is dissipated with this kind of hardware is quite low due to the fact that it is non-volatile. So is there anything more that we can do on top of this? So we have seen, so from these works that we see here, we know that NVM is good for processing in memory using its analog computing techniques, but can we go one step further and introduce more operations that can be done on this hardware? So this is what we're trying to address in this work particularly. So to give some introduction into this problem, I think we can also show it very clearly. So I think I can quickly go over it. So we have this what we call a learner. This learner consists of a pre-trained and a meta-trained controller. And this process of pre-training and meta-training, Mikhail introduced to you in his talk. And we have this other piece of hardware, which we call the explicit memory. And here in this talk, we are mainly focusing on the implementation of the explicit memory. So these are the two pieces of the learner, and this learner gets exposed to new class examples, a few of them, and then in each of the sessions, it gets some examples from new classes. And yeah, so these are few examples of the classes. So this is why we call it few short continual learning. And at the end of each session, we get some queries covering classes, not only that were exposed during that session, but also all the previous sessions. So then the task is to classify these queries to this correct class that it correspond to. So we do this by feeding the query image through the controller and getting the vector, a query vector, which can be then used to do some similarity calculation. And here we discuss what kind of operations we are proposing to do on this in-memory compute hardware that we want to that we'll show in the next slides. So the first operation is the expansion of the explicit memory. So this happens when you get a new class vector, an example from a new class vector for the first time. So here we want to then allocate a new space on the explicit memory. And this will be one of the operations. The other one is physical superposition inside this explicit memory. So this happens when we get a second or any subsequent example from a class that was previously exposed to. And we send it through the same controller, and the resulting vector we try to somehow superimpose on the existing information in the explicit memory. We'll see in the later slides how this is exactly done. And the third operation is the similarity search operation. And this is where when you get a query, it generates this query vector, which can be then used to compare against all the vectors that are stored inside the explicit memory. And this gives us the predicted value, which is the result we want. All right. So far we have seen what operations we want to implement in the logical abstraction level. And in this slide, I'm trying to show how we map it, particularly this explicit memory into its into a physical realization of this explicit memory. So at the heart of our physical realization is a cross-bar array, which you can see here. It consists of memory devices. In this particular work, we actually look at one type of memory device called phase change memory device. I'll discuss more on the properties later. But then the next thing is that we have a few interfaces. One is to send the support vectors, which correspond to the training examples, through this programming circuit to program into the different columns. And then we get the query example, which is sent through a PWM circuit as time encoded pulses, which will give us some currents that are accumulated in the columns, which can be digitized to get the predicted result for an inference task. So internally, going one step deeper into the hardware stack, we see at each cross point we have is a phase change memory device, which has different conductance values. We'll see each other in the more detail in the next slides, but the idea is that we will manipulate the conductance of the devices as we get exposed to new examples from a given class. And this is the operation that we want to perform to achieve what we call this in situ accumulation. Okay, so now I think we can look in more detail how this programming methodology itself works. So that is when we get a support vector through the pre-trained meta controller, the support vector, then we have to map somehow into the crossbar array. Support vector itself here, we consider a crossbar which has a size of 256 rows and 256 columns, which means that the support vector we produce is also the same dimension, and they are bipolar vectors. So basically, when the support vector arrives into the programming circuit, it will select a column based on the class that it belongs to. And in this case, it's seeing this object of this class, of the cylinder class, for the first time. So it allocates a row, a column which has not yet been programmed. So at this point, it's good to cover some basics of how the device conductance changes in the phase change memory devices. It basically has two main states. One is called the set state, where the atoms or the atoms are organized in a more crystalline fashion. And then there's this amorphous phase where it have some disorderly configuration. By applying a reset pulse of this nature, we can bring the crystalline device into amorphous state. By applying what we call a set pulse, which is of this shape, we can bring the device into a more structured crystalline state. The crystalline state has a high conductance, and the amorphous phase has a low conductance. Now in this work, so these are so far we have seen, these are so far what we have seen in the literature, how these PCM devices can be manipulated. In this work, we explore another idea, which is called the partial set pulse. And the idea is that instead of applying a full set pulse, we are trying to bring down the magnitude and the duration of the pulse shorter, such that the process of crystallization is not completed. So in this case, we end up in a state where it's become slightly more crystalline, but not completely crystalline. So this is the type of pulses we want to explore in programming the devices here. So we have this reset device, column of reset devices, which is achieved by applying this reset pulse that I showed earlier. And then when we get the first vector, when we have a +1 element in a given position, if this condition is met, we will apply this partial set pulse on the corresponding position. And this will change the conductance values of the devices in this column slightly towards the set state. But now the question is, how do we accumulate more support vector instances of the same class? So we just saw one example yet. So let's say we get the second example. What we do is we will continue the same operation, which is we look at the ith element of the new support vector, and if it has a +1 in that position, we apply a second partial set pulse to that particular device. And this will give us a new state to the devices in the column, which represents the accumulation of the two support vectors from the same class. So in this way, we are, instead of doing the accumulation explicitly by exploiting the analog properties of the devices, we do this as an in-memory or in situ accumulation operation. The next question is, how do we accumulate on the negative direction? So far we have seen if we get a +1 component, how we treat that. But as I said earlier, the support vector consists of not only +1s, but also -1. So this is bipolar vector. So if we see a -1, what do we do? So it's not easy to apply a partial reset pulse due to simply the dynamics of these devices. So, which means that we have to operate with two devices, so in a differential configuration. So in each of these cross points, what we have is not just one PCM device. In reality, in this work, we have two devices, one representing the positive component of the vector and the other representing the negative component. So then we can apply a -1. If we see a -1 in the support vector, we can apply as a partial set pulse on the negative device. If we see a +1 on the support vector in a given at a given position, we can apply the partial set pulse on the positive device, and then we can continue this process over and over for a few more iterations as we see new examples of a given class. Okay, so far we have seen how the programming works on the crossbar array. In this slide, we try to show at a very high level how the similarity search works. So the crossbar array that we have, as I said earlier, is a 256 by 256, and it supports the application of PWM pulses corresponding to query vector at the resolution of a maximum 8 bits. So that due to this reason, we apply it as 256 values, each of which has 8-bit precision. The resulting currents that we digitize also becomes 8-bit numbers. And also because of the bipolar nature of the devices or the unit cells that we have with the cross points, and also due to the fact that the PWM pulses are also applied as either positive values or the negative values, so these are signed values, we apply it as a 4-quadrant read. So we do evaluation of the matrix vector multiplication for the positive components of the positive input versus the positive device values, and the positive input versus the negative device values, the negative input versus positive, and the negative versus negative. So this way we evaluate it 4 times, giving us a total read time of 512 nanoseconds. And at the end of it, we get this 8-bit vector, and each class will have a value in this vector, and then we perform an argmax operation outside the crossbar array to get the final prediction value. In this slide, I'm showing the experimental setup. We have here an FPGA, a development board with an FPGA, which can then communicate with the host computer. And the FPGA can also communicate with the onboard 2 cores that are on the same board. So here we see core 1 and core 2. So each of these cores are in memory crossbar arrays. And for this work, we only used one of the crossbars. So you see more details on how the content of the crossbar looks like as we progress with the different stages of the experiment. But yeah, here in this picture, I'm showing the die micrograph of one of the chips. Here, so it has in the center, it has this PCM array, and then the other peripheral circuitry that I showed in the previous slides. So initially we get the training examples and the training labels, which goes through the controller and then bipolarized, and these then go to the as programming commands to the array, and the columns of the array get programmed. So at this stage we get programmed array of programmed devices, and then we can send the query examples using the same controller, quantized to 8 bits, and then send them as matrix vector multiplication commands. The resulting MVM output is kind of collected and used to evaluate the accuracy. So for other session, we can again send more training examples. So this is just for one session. So if you have in the continual learning phase, we have more sessions, and we can send more training examples and program more columns and do the accuracy evaluation on each of the sessions using the same process. Here I'm showing you the experimental results of the programming technique that we use. So starting from this reset state, when we apply, to get the reset pulse, we apply a pulse of this duration and magnitude. And from this state, we can move the device towards the crystalline state by applying the partial reset pulses of this particular shape. And then how the conductance varies across all the devices in the array is shown as error bar plots here. Starting from the zero conductance, we slightly move on average, getting to higher and higher conductance states as we apply more and more pulses. So these here represent the conductance state of application of different pulses, and here it has the representative figure of the state of the structure of the device at each of these stages. So based on this knowledge that we have gathered so far on how to program the devices, how they program it at the array level, how can we bring this knowledge to run an experiment involving a large data set and evaluating the accuracy, such as image classification. So here we use a data set which is CIFAR 100 for this evaluation, but we also evaluated on mini ImageNet dataset. This consists of, for the few shot class incremental learning problem, it consists of 100 classes. The base session has only 60 classes. And here we see a portion of the crossbar array, the device conductance values. As we program the part of the crossbar array corresponding to the first 60 classes, and this is the first example from the 60 classes. See the device conductance in this arbitrary unit that we're showing changes from -80 to +80. So here we see it slightly getting more and more towards achieving higher matured conductance states as we introduce one shot at a time. And then when we introduce 5 shots, we've seen that the conductance evolved to a more and more mature states in either directions in the selected columns for these 60 classes. And then we can continue with other sessions. So in this session 5, for example, here we see adding 5 classes, and the examples from these 5 classes from this class 75 to class 80. And here in this green box, you see how the device conductance evolve for these 5 classes when we apply the 5 shots selected from the classes. And the end, we see for the final session for the classes going from 95 to 100, how the array gets programmed and the device conductance look like, and the evolution of the conductance at the end of the final state of the experiment. In this graph, we are showing the classification accuracy, and this here is the baseline accuracy, which is exactly matching with the result that Mikhail presented. So this is the baseline software. It's just the algorithm implemented on the software without any noise. And with this red curve, you're seeing the impact of implementing the same algorithm, but in this at this time we move our explicit memory to this analog AI hardware that I showed earlier. So because of this noise that we've seen, that we experience on this hardware, our accuracy is obviously reduced by a couple of percentage points. But compared to the other works that are in the literature, which again, what Mikhail showed, presented in CPR 2020 and NeurIPS 2021, our hardware results, even with the presence of noise, are performing better. Yeah, so now let's conclude the work. So far, what we've shown is a hardware for continual in-memory learning, a continual few-shot learning using in-memory compute hardware. And where we differentiate from others is mainly from this being able to doing the in situ accumulation operation, which comes freely without having to explicitly spend operations on that. And we have also the support of multi-bit analog now. Being able to accumulate more and more states means that it's now multi-bit explicit memory. We can also perform the search operation in one step. Coming to more quantitative numbers, we see that our method supports a particularly when it comes to the programming energy, we are performing much better than the other works that are in the literature, mainly due to the fact that we do not program the programming works in an incremental fashion, which allows us to save some energy on that. Yes, from here, I think we can quickly show you a demo of how our platform looks like, and for a selected some selected subset of classes from the Cypher 100, how we want to show the concept of in-memory continual learning. I hope you enjoy this. Hello, in this demo, I'm going to show you for the first time how few-shot continual learning can be done on in-memory compute chip. This chip was developed at IBM Research Zurich Lab. We are using images from Cypher 100 dataset. First thing we do is we select classes. We are using animal classes. For example, we can choose elephant as our first class. And what we do next is we are going to feed a few training examples from the elephant class one by one through a neural network. The neural network is pre-trained and meta-trained. The result of the neural network is a high-dimensional vector representation, and we are sending these vectors one by one to this in-memory compute chip. Inside the chip, it will select one of the rows on the array, and then they get programmed using partial crystallization set passes. Then we select the second class, which can be something like wolf. Similarly, wolf images are fed through the same neural network, and the array is programmed. You can see how the conductance of the devices on the selected rows varies to represent the vector updates. At this moment, we can query our learner from query examples from, let's say, wolf class, and we can see that it gets 100% accuracy. When a query image is given, similar to the training images, they will be converted to a high-dimensional vector and applied as voltage pulses on one side of the in-memory compute array. The resulting similarity vector is received on the other side. However, if we evaluate the learner on images from a different class, for example, like leopard class, having seen no images from this class so far, the learner will misclassify it as either elephant or wolf. To enable continual learning capability, we just need to feed in a few training images from the leopard class. Once a row on the in-memory compute array is programmed to represent the leopard class, we are able to successfully classify the leopard query images. We are very excited to bring this new technology to a wider audience in the near future. All right, with that, I will wrap up my talk. So we are glad to take any questions.
Thank you, Geethan, and thank you for the great demo. So now the floor is open for questions.
So Geethan, I've got a question. It's Graham.
Hi, Graham.
So you with the variation of conductance across the device, when we've done this in the past with large binary vectors, the distributed representation of the vector has helped because the variation in conductance is sort of averaged out. Can you do something similar with these real valued vectors?
So if I get your question right, so the previous works that we considered as a collaboration, right? So there we try to program the vectors in the binary as a binary vectors. So basically just exploiting the two states like the set and the reset state. So in this work, we are going one step further by trying to also look at how the multi-bit programming on the device works. Yeah, I think it's orthogonal to what we explored so far in the previous research.
Okay, I just wondered if there was a way of reducing, or because the device itself has varying conductance across it, whether you can do something with the vector representation to reduce the noise.
Across the device, you mean if there's like a systematic noise?
Yeah. I mean, the conductance across the device varies anyway, doesn't it?
It is, yes. But now in the previous hardware that we looked at, it had some kind of a systematic noise across devices. And then we had to, because of that, have to do some kind of random placement of the vectors.
Yeah.
But in this new hardware, we are using, it's no longer there's a systematic noise. So that means that the need for a random placement of the vectors or the components of the vector is no longer required.
Okay, thanks. That's very interesting. Thank you.
We have one question in the chat. I guess it's more for Mikhail, but then I mean, feel free, Geethan, to contribute. Have you explored out of distribution detection if leopard similarity is insufficiently similar to any elements in the dictionary to add?
Yeah, so
yeah,
maybe I can quickly. Yeah, so like as for now, we mainly stick to those standard benchmarks in future class incremental learning. But of course, it would be like an interesting next step to take, yeah, to do like out of distribution detection, for sure, yes.
Yes, just one clarification question before I give a turn to the next person. Do you select the samples randomly? I mean, the ones you insert in the memory?
Yes, well, yeah. I can answer that question. So we have in the base session, right? For example, we had those 60 classes, right? And there overall we have 500 training samples per class, and we select randomly a certain subset there. Yes.
Okay.
But then the rest is really given by those data set, like those splits from the tasks, from the future class incremental tasks. So you always get the same 5 shots per class. Yeah.
Okay.
That's given, and of course, yeah, there you can also optimize, right, by selecting support samples, which where you can then afterwards discriminate better, like which are really representative of those classes, and enable good discrimination.
Yeah. Okay. Sohum, now it's your turn. Please speak up.
Hey, can you hear me all right?
Yeah, we hear you.
Yes.
Hey, thanks for the talk, Geethan and Michael, and thank you for the demo as well. So I had a question. Could you share that slide with the energy numbers for the associative search? I think you had one of the slides.
You want to see it now again, or?
Yeah, so I saw some number there in energy per associative search. I wanted to ask you, that was like 25 picojoules or something, or maybe 20 picojoules for you, right?
Yes, so it was.
So the question is what? Yeah, go ahead. I remember the number, but the question is, was it associative search per bit? Was it associative search of one vector versus 60 classes, or like how did you calculate that number? How did you measure that number?
This is because like with the different sessions, we have different classes. So this is always normalized to the dot product similarity, like a energy per dot product operation.
Energy per dot product. So if you want to get a per bit number, then I should divide by the dimensions of the vector?
Yes.
Or I'm sorry, per element, not per bit, because you're doing multi-bit here.
Yes.
Per element, right?
Correct.
Okay, yeah. Got it. So the other question is, so you have 256 elements.
256.
elements times something like what 60 classes, right? So that's about 15,000 numbers, right?
Initially, yes, and then at the end of this experiment, we have 100 classes.
So about 25,000, less than 30,000 numbers total, right? But if I'm looking at the entire inference data part that you have, that includes your feature extractor, the fully connected network that's translating these feature activations to prototype. If I remember, there's some sort of an activation memory as well, which I'm not sure where it is.
Well,
and
I mean,
then finally these 25,000 numbers. So looks like the numbers of like the amount of computation there is probably much larger than this associative search over here, right?
well, I mean, I agree with that energy for the controller in terms of the number of operations can be higher, but the goal of this research is like exploring the explicit memory part of the architecture, because there have been previous works showing how the feature extractor, which is basically a convolutional neural network, which can be for an inference task, how it can be implemented on a cross-bar array or in-memory computing arrays. This has been shown previously by other people, or even from our group. There have been some papers on that. So the goal of the this research was mainly to focus on the explicit memory part of this, which is kind of the novel paradigm we want to explore. And also regarding the activation memory, this is not used for this mode that we are operating on, which is the mode 1, where we do not want to do any updates to the fully connected layer, nor to the feature extractor. They remain frozen for the whole operation.
I see. So no, I didn't mean to say that. I understood your motivation. That is the focus of a very efficient implementation of the EM module, right? Just the EM module. But what I was trying to get at is that what is it that you expect this improvement? We've got a certain X improvement in EM module. So now you've reduced your energy expenditure in the EM module by a large fraction. I'm hoping because of the PCM, right? So what do you expect for the entire energy budget to change? Because if the majority is in somewhere else, right? I was trying to get an impression. Is it going to be a large change? Is it going to be a significant change to the total thing? So any arguments, any comments?
Yeah, I mean, so you want to know like I cannot tell you off the head just roughly.
I see. So you don't have any estimates? Yeah.
Any estimate? No, we didn't look at it. It's just that because the controller itself depends on the complexity of the data set that we are working on, because for OmniGrot we have one controller for one certain architecture. For the mini-midget and the Cypher 100, this is completely different, and because of that, this is like a pluggable module for this work for as far as this work is concerned. the controller, so there we leave it to be like something that user can decide based on this data set, and that's why we just focus on this explicit memory part.
So understood. So could you tell me the complexity of the controller? I mean, by how many weights do you have stored there?
Well,
maybe,
Michael,
I don't know.
Yeah.
1 million.
So that ResNet 12 that we use has around 11 megabits. Weights. Kernel weights.
11 million.
But this is not optimized for the direct mobile application yet.
So these are float 32s or int8s or
float,
BF16. What is the format again? Float 32?
Float, yeah, float.
And so that's just the feature extractor, right? What about the translate, the fully connected network?
That one is not too big, right? This is just 640 by 256 in the case of Geethan, right?
640 by 256. Got it. So it's like we're close to around 1 million, basically.
Yeah.
So
this is manageable, but overall, this is really like those, as Geethan already said, like these feature extractors are not yet optimized, and probably you could also simply replace it by a much more efficient one in terms of weights and number of ops which are needed. So that's
got it. But what you have,
especially given the complexity of those tasks, yeah, should be possible.
Right. But what I was trying to get at is that that's about like 5 to 15 million range of some numbers, and you've got 25,000 on the EM side, right? Something like that. Looks like that's the split. Got it. Okay, great. Thank you. Yeah, this was very helpful. I just this was not clear actually, so I wanted to know about this. Thanks a lot.
Yeah.
Thank you, Soham. Yeah, sorry.
I have a question.
Yes, please go on then.
Guys, thanks a lot. Exciting projects. Probably, I don't know, it's not a very intelligent question, but I'm curious, like, what are you going to do next? Because these impressive results, like you've achieved state of the art now, are you just going to like leave it there, or do you have plans on like extending these projects? So basically, is there any roadmap for this direction now?
I think Abbas would be the more suitable person. He unfortunately not here because he had to travel to Iran. But yeah, I think from internally from IBM side, we have like a certain structure that we have organized for the research projects, and how we lay out the plans for a year horizon of 1 year, quarters, and things like this. So we internally provide updates each quarter, how much progress we make, and then get the feedback from higher management and continue to revise the targets, and these kind of things are going on. But I don't know any plans to come next. Yeah, as far as yeah, from my side, I don't know how much we're allowed to say about it.
All right, I mean, no worries. I mean, if there is, you know, if it's not clear whether it can be shared or not, yeah, I was just curious, you know, it was just out of, you know, general curiosity.
Sure.
But I remember, I mean, Mikhail, this work that you have presented, it was published previously, right? In this memory augmented. I mean, you gave a talk previously, or it's another.
This was Geethan's talk.
That was Geethan's talk, yes.
Yeah, so this like yeah, it's slightly related to what we do here. So back, maybe Geethan even can explain it better, but back then we applied it mainly on few-shot learning, and there also like the structure of the memory and the content was different, right?
Yeah, sure. And here it's continuous.
And here we have continuously evolving memory.
Yeah, I see. Okay. One reflection on Geethan's part. So to me, when you presented, it appears that you're kind of, I mean, the fact that you're using bipolar representation is now kind of look more and more artificial, so to say, because you do operate on fractions, you know, fractional values of vector components. So why don't you, or do you have any plans to convert into HRR, say, totally?
I mean,
you can change connectivity in small fractions. You don't need kind of this +-1 increments. So,
yeah, but the idea is that we need to identify a small step in either direction, right? So that's this one +1 and -1 represent that small step, that, or the delta that we want to.
So you cannot control the increment. So for example, with the pulse of certain duration, you can increase more a component than just on a fixed fraction.
Yeah, the thing is that the pulse duration currently, as I said, showed earlier, is like 5 nanosecond is the peak time of the pulse, which is kind of the limit that we already reached there. So we cannot bring it even more lower in the duration with the current hardware that we have, the current hardware that we have. Cannot make the duration shorter, but maybe in a newer hardware or the next generation hardware with a more like a precision in encoding the time encoded pulses, maybe we can try to reduce that pulse duration to get even more fine-grained incrementals to the conductance of the device.
Okay.
There was one more question in the chat
Yes.
about orthogonality. So yeah, maybe I can quickly read it out. So with respect to the omniglot dataset, is each symbol orthogonal to each other letter, or are letters from the same language allowed to be more similar? So in general, with our loss function, we try to embrace orthogonality, but still, of course, there can be relation between vectors, right? We just try to keep them as orthogonal as possible, but we don't, for example, assign fixed vector for different symbols, and they cannot change in terms of relations, etc. So yeah.
Yes.
Yeah, I think the question was whether more about the letters from the same language, whether we want to allow them to be similar, more similar. The answer is no. We don't have that kind of a constraint to make letters from the same language similar. It's just based on the visual features of the letter. It will get assigned to some kind of quasi-orthogonal representation. But across different alphabets, we have noticed that there can be some similarities. For example, the letter O in the English alphabet can be, it's just a circle, right? So there can be another language where it also try to represent a character with a simple circle. And there, in that way, there can be some similarities between characters which we cannot avoid. But we don't try to impose any kind of a similar or non-similarity constraints on letters from the same alphabet or different alphabets, but it's just the controller will do that for us.
We have a quick question from Sohum. Please.
Sure.
Yeah. Sorry, can
yes.
you hear me?
Yes.
Yeah,
Yeah.
now I can hear you.
I think I was muted in the middle. Yeah, thanks for that. So I wanted to ask you, so now you are starting with 60 classes and ending up with 100 classes, right?
Yes.
So increase is about 50% of the initial
Yeah,
number
more or
of classes that you've begun.
Mhm.
If I'm thinking, if you want to start with 50 classes, let's say, and reach to an order of 1,000 classes, right? So you'll have far more sessions of retraining. Do you see this breaking down? Do you have any hunch or any arguments that this will be stable, or that it could start falling apart? Anything that you've seen in your experiments so far?
So falling apart in the sense the accuracy that it achieves?
Right, your accuracy is degrading slowly as you are adding more classes. So it's not like it is slowly forgetting. Maybe it's one way of saying that. Do you see that forgetting, sort of catastrophic forgetting to become even more pronounced and perhaps starting to forget rapidly as you increase newer classes?
I wouldn't think there will be a drastic drop in accuracy at a certain point. I don't know, Mikhail, what do you think? But considering also the omniglot dataset performance that Mikhail showed, right? There we go up to 1,600 classes. And
yeah, but it started with 1,200 there. So that's not really.
Okay, yeah.
To me, really, rather the limiting factor will be that we have such a low number of classes in where we can method on our controller, right? If we really don't show that diversity between different classes, it might be not prepared to distinguish between completely different classes or recognize completely.
So any
classes.
shifts in the go ahead.
Yeah, no, that's actually it. Yeah. So I doubt that. So if you have a sufficiently large base set where you can meta-learn your controller well, the feature extractor, then I think you can also add more classes in the end. But going down on the base classes might hurt your overall performance rather than just extending the novel classes more.
So it's interesting that you didn't say that we could increase dimensions and make it better, or the problem will.
We updated on the dimension, and there it depends on which mode you use. Interestingly, for example, for mode 3, a lower dimension was more helpful than the large dimension, so it might also end up in a bit of an overfit. But with mode 1, 512 worked the best. But even going to higher dimension, maybe the number of classes was in our experiment still too low. So maybe with a higher number of classes, it might be beneficial.
Okay, got it. Thank you.
Okay, thanks.
All right.
I have a quick.
Yeah, sure. Go on.
Just a quick one.
Yeah. Hi.
This is when you use bipolar representation, and you have both one for the negative and the other for the positive values. Of course, eventually both of those will saturate. But I think you certainly mathematically you can just count a bit bipolar, just binary, and you need one extra counter that tells how many times that particular thing was written into. So you use half of that as the threshold. So I don't know if it's physically possible, but mathematically it's equivalent. In other words, stay in a binary and have just one extra resistor, varying resistor, and increment that every other time, and that's your threshold.
Actually, I think that's a good suggestion. We've also thought about the scenario where the different classes get not the equal number of examples, but different number of examples. In this case, also we have to do some kind of normalization by having additional resistor, remembering how many examples that you were given per each class, so that you can do some kind of post normalization of the result that you get. But certainly this kind of idea mathematically it seems equivalent. Yeah, I mean, something interesting to consider. Yeah, thanks for the suggestion.
Just like to stay in a binary as far as possible. Okay, thank you.
Thank you.
Thanks, Fenty, for the question. Well, probably now it's time to wrap up this session. So I would like to thank once again both Geethan and Mikael for the great talks and the demo. So we'll definitely keep in touch and follow up on your development. So that's great. Thank you very much. So see you in 2 weeks from now.
Thank you, everyone.
Thank you.
Bye-bye.
Yeah. Bye.
Thanks, everyone. Bye.
Thank you, everyone. Bye-bye.